This is the second presentation by Aduro. So in this presentation, you will have Ofer, Mena, that you've seen in the previous video, and also Anil, who's the chief scientist for Aduro. And this presentation will focus more on the chemistry behind it, so it's a little bit more in detail than the prior presentation. So with that being said, I hope you enjoyed it.
Hello everyone, I'm Anil Jawar, Chief Scientist with Aduro Clean Technologies. I have been working with Aduro for past 9 years and working on development of the project in coordination with our Chief Technical Officer, Mark Stristed. I also manage the team in Sarnia in London. I was doing my postdoc at ICFR, which is an Institute for Chemicals and Fuels from Alternative Resources. It's part of a Western university. I was at the time working with Dr. Cedric Brians and Franco Beruti, and Ofer, like as Aduro came for a project on heavy oil upgrading. They had a patent and they wanted to experimentally verify some of the results. And I was the lead from ICFR working on that project. That's how I started. And basically, as I progressed my work, like we started working into different areas and bridge into renewable fuels and plastic.
There is more because I want you to speak about the team and your experience with the team and the evolution, but we'll keep it for maybe a little bit later. Hi, everyone. So the way we plan today is that by way of presenting maybe 3-4 slides. Those are very directed slides that I will ask Anil to comment on. The slides are speaking about a little bit about our technology in comparison to the mainstream, which is a pyrolysis. Later, a little bit about our technology in particular, and moving forward from the technology, once you have a grasp of what we've been doing, a little bit of how you can manipulate to create different type of product. Beyond that, I think we want to keep this informative for you, to keep it very focused on one hand and to allow you later to ask questions. So I mentioned yesterday that the technology is very, very different from the mainstream technology, which is a pyrolysis approach, basically the thermal approach. This is what most of the technologies that I've showed you before yesterday on those tab of thermal, most of the technologies are somehow associated with a thermal operation. One of them mainly is pyrolysis. This slide in particular will present you a little bit what is the energetic that is required to work, what happens there. And later in comparison, you can see where our technology reside. But Anil, I'll give the stage for you from here, and maybe you take the audience through this slide.
What you're seeing here is called energy profile diagram. Here, what we are talking about is ethylene and polyethylene formation and deconstruction. So anything you take in the universe possesses a certain form of energy, which is called Gibbs free energy. So here, the ethylene molecule, which is like a 2-carbon molecule attached to each other, it's a hydrocarbon, which is a feedstock for making polyethylene. So it possesses certain energy, and you can see that it's a little bit higher than polyethylene itself. So what happens is ethylene itself is a very stable molecule. So if you were to put ethylene in a cylinder and compress it and keep it for years, it's not going to react on its own, because it has to overcome this hump, which is called activation energy. And in order to overcome this hump through polymerization chemistry in presence of catalyst, basically what happens is ethylene reacts to form polyethylene by releasing enormous amount of energy. The energy content of polyethylene is much lower than ethylene itself. So that's why polyethylene is much stable, and it's not a reversible reaction. That means you cannot just take polyethylene, convert back to ethylene without applying any form of energy. So what happens is polyethylene is very low energy. Now, for chemical recycling, we need to provide the energy which was released during the formation of the process. So in case of pyrolysis, what it does, it uses thermal energy, basically heat, to break apart the polyethylene back into different compounds. And this process is very random. You're just using heat energy, and it breaks the product at different chain lengths. The product form is very complex mixture of diverse chemical functionality, and it also has a lot of unsaturation. The product obtained from pyrolysis has higher energy content because we are applying that enormous amount of energy. So they are also unstable, and they will decompose over time. And what Aduro has done is developed a process called Hydrochemitic Technology, which basically uses catalyst, hydrogen source, water, and it only needs a little bit of energy. So it releases an enormous amount of energy, but the energy required for breaking apart polyethylene is much less than those required for pyrolysis. That's why the energy content of the product is lower. And since we are using an in situ hydrogen source, the product what we get is mostly saturated hydrocarbons. When I say saturated, they are more like paraffin, waxes kind of thing. And what they don't have is like a double bond, which you see like in ethylene. They don't have it.
So Anil, to the audience, I'll say that it's just a little bit more purified material with less problems inside, with less functionalities, and it resides well as a pure stream that you can immediately process,
Yeah.
in a cracker, rather than pyrolysis, which would need a lot of work at the back end just to bring it to that stage, which effectively means more energy, more cost, things of such.
And also, the product doesn't go any side reactions or polymerization when we apply thermal energy or anything.
Right. Well, what doesn't tell to the audience, what it means to the audience basically is that when you act with pyrolysis, the material is very reactive, and it requires immediate treatment. With us, it's very, very stable basically, and it's ready to go. Anil,
sorry, Ofer, is that I just want to translate that from a business standpoint. That translates into higher output, and that yield that we're achieving has a higher value compared to the quality of pyrolysis oil, correct?
Yes.
That's correct. And apart from that, in pyrolysis, what happens is because you're using enormous amount of energy, the liquid product, which is a desirable product, the yield is less than 70%. And of that, the only usable product is about 20-25%. Whereas in our case, the yield is 85% plus, and the usable product is, our process is very tunable. So depending on if you require like a naphtha cracker feed, we can increase the severity of the process and get a carbon number range towards the naphtha cracker feed.
We're trying to translate chemistry to cost and performance, guys, for you to understand. But basically, what you see here on this slide is higher energy of those thermal operation, lower energy of the Aduro operation. Effectively, it means lower cost, and because of the nature of the pyrolytic process, it requires additional post-processing treatment, where in our case it doesn't. Everything resides in the reactor, and so we save a lot of capital costs. This is basically the window to do smaller system. This is the reason why we can do smaller system at higher yield, basically. So this slide is a little bit about our secret sauce. Anil, if you want to speak a little bit about what is it that we're involving specifically on this hydrochemolytic, what is it we're using?
So our technology is called Hydrochemitic Technology. It's a combination of two words. Hydro means water, and chemolysis means chemical deconstruction of molecule. And the way we do that is this process is like a unique chemical conversion process, and it uses metals which are readily available, low cost, and recyclable. So in some cases, we can just use the wastewater from heavy oil heavy oil industries as a source of catalyst. We also use what we call is hydrogen equivalents, which is nothing but oxygenated substrates such as glycerol, cellulose, or some of the components from waste plastic, such as from PET. We can get ethylene glycol, which could also be used as a hydrogen source. So since we are using these compounds for reduction of or stabilization of the product, we don't need any kind of molecular hydrogen, which is the limitations of other process. We eliminate that, and we don't need any infrastructure related to hydrogen. This process is highly efficient. It operates at temperatures less than 375 degrees Celsius, which is much lower than that of pyrolysis or gasification. And as we talked about, like the product is of high functional purity, which I mean we can get saturated paraffins or alkanes. This process is capable of recycling waste plastic which are difficult to recycle, such as what we call is plastic can be divided into two types, chain growth and step growth. So when I say chain growth, it's a single molecule such as ethylene. They are kind of repeated to form that polymer. And in case of step growth, the example is PET, which is formed by the combination of two molecules, which is terephthalic acid and ethylene glycol. So PET kind of polymers are easy to recycle. So that's why you see there are many technologies addressing those. But when it comes to chain growth polymers, they are very robust and are difficult to recycle. And our technology is answer to those. And
well,
what we can...
I'll stop you there for a minute and just try again visualize functionalities in terms of value and cost. So for the audience here, we talk about a little bit yesterday about the finesse that the system has in terms of using things that are already available and their impact on the capital costs. So in the heavy oil, we basically increasing the percentage of those catalysts, and those catalysts are available, and we can take them and find them and bring them into other processes. But we will only introduce what we call the glycerol equivalent or the hydrogen equivalent, which could be cellulose or ethanol or glycerol or material of such. And so the system is effectively, because everything happens simultaneously in the system, and we'll show you this later, it means it's a very, very basically efficient system. Also, we only address in the heavy oil material that actually we need to deconstruct. So our pre-treatment basically is very, very simple. What we do is we separate the heavy oil from the light component, that there is about 75% light component that does not need any chemistry. And we stay with the stubborn material, which we call this asphaltene. And so you can understand right there how the system is so efficient, not just that the technology is efficient by itself, but us working just on the asphaltene is basically 25% of a barrel. We don't process the whole barrel. What we do later is just, once we're taking care of it, we mix it all together and we bring it back as a new synthetic crude. But that also speaks about the finesse in the renewable side, where in the renewable oil, we'll consume the glycerol for us for hydrogen purposes, and we'll only bring the metal into it. And the metal can be recycled and they be collected in the water. And because of the low thermal activity, those metals can act again and again, many, many times, and they are low cost. So a lot of what I'm telling you now reside in a low capital cost system that you can do it again and again. It's almost speak to the configuration that technology can be built. And the other beautiful part of it is with respect to the plastic, is that we can take, as Anil mentioned, certain material from the plastic, such as plastic bottles. When we do the deconstruction, when we run them through the process, we will take some of this material, which is called ethyl glycol. It will be our hydrogen equivalent. And again, we'll do our run with some metals. And so a very agile system that can, in a way, there is a reason why we put a visual process, a vision of ocean cleanup, where we think this system could be such a small that it could be on a vessel and could move around and be a very, very efficient and live by the waste basically while acting as cleaner. Because of the efficiencies, the chemical efficiencies that we are promoting, there is multiple of environment benefits. So environment benefits are because, first of all, the footprint of the system is, if you're using high efficiency, then you're using less CO2 in general. And on top of that, of course, because of the systems can be deployed in somewhat remote areas, then you avoid a lot of negative impact costs. And it's right in the transportation for the plastics, and this is right as well in the heavy oil, because heavy oil, basically you have to blend it in order to transport it. It's right when it comes, you either do something with it or you blend it, and now you're curing cost basically to the system. So we're showing you a little bit of the, open the curtains and show you why our claims are as such, where's the confidence that our claims, can be achieved, because they are distinctly different from whatever is out there today. We know very well what is out there today, and this is a basically different direction and approach. Because of that, it opens a lot of business opportunities. I will, Anil, do you want to say something before we move on to the next
Yeah,
slide?
I also will say that what this is called is our technology is a platform technology. So it has a flexibility. We can apply it to like heavy oil, plastic, and renewable. These are the three areas we have explored so far. And I believe there are further more applications which we need to explore.
Yeah.
One example could be like pyrolysis oil,
Yeah, or right now we're talking about, we don't talk about pyrolysis oil here. We will talk about more of a future immediate, like rubber tires or lubricant used oil, but that's basically, but many unused options that share the same chemical concept that we can address basically.
Yeah, so a little bit of chemistry. So this slide talks about how ethylene is produced using ethylene cracker or naphtha cracker, and also formation of polyethylene. And then we'll talk about how we can deconstruct polyethylene for chemical recycling of the product. So naphtha or natural gas liquids. So when we say naphtha, those are hydrocarbons which are called paraffins. Their carbon number ranges from C5 to C12. Or natural gas liquid, which is nothing but liquid methane, or ethane. They are fed to ethylene cracker, and what they produce is ethylene. Ethylene is a two carbon molecules which are attached by double bond, like two bonds. It's an unsaturated molecule. The N here in the equation represents that there are a number of them which are produced. So ethylene itself is very stable, as I explained earlier. So they don't react on their own, but under the polymerization chemistry, in presence of catalyst, they react to form a linear chain molecule called polyethylene. And again, depending on number of carbon molecules or how they are arranged, we can get different grades of polyethylene, such as low density polyethylene, high density polyethylene, or ultra high density polyethylene.
Anil, do we care in the system if as long as we're processing polyethylene, do we care in the system if we are having low or high density polyethylene?
Not in our case. So our system is not dependent on what kind of polyethylene. So as long as we have what we call is polyethylene in any form, like it could be cross-linked, high density, low density, or ultra high molecular weight polyethylene, the system is not affected by the quality or the quantity of it.
And the chains that we are producing, can you speak a little bit to the?
So what happens is at the end of life, the polyethylene, like which are not mechanically recycled, we can subject it to our hydrochemitic process. So it works like a chemical scissors, as I said, like in presence of water, catalyst, and process condition. It randomly chops the polyethylene molecule into different molecular weight. The carbon number ranges anywhere from C8 to C100. and the average carbon number being about C25. So when I say average carbon number, it's like most of the carbon atoms. Like if you take C10 versus C100, like the average will be around that.
So,
And
Anil, sorry to help you to stop there. For the audience, the longer the chain, the more heavier the product. So longer chains will be oil that could be used for recycling, for our production of new plastic, and shorter chains will be closer to a diesel product. And we'll show you a breakdown of those chains in a minute,
yeah.
but just to give you an idea. That means that the product, the shorter the chains, the lower the value. The higher the chains, the higher the value, because you can do more things with it. You open yourself to more things. It's at the end of the day, it ends up as an industrial commodity product that has a value in the market. Currently, when we're talking about taking waste polyethylene, which may cost, as Mena mentioned, $200 or less or more, when we finish working on it, we'll have a barrel of material that's worth, well, a ton of material that's worth close to $1,000, depending on the demand. It could climb up to 1,300, and between 800 to 1,300, really wide range. And because the demand for recycled product is increasing, organization wants to continue and mix that with the regular oil, so they could sell product that says this is with recycled product. Us building those units independent to centralized locations, and we're basically providing another income options to someone that until today had to pay to get rid of it, basically.
And also, I would say that the process is very tunable, right? So we have different controlling parameters, such as temperature, pressure, space-time, which is like how long you want to heat the process. So depending on that, we can tune the carbon number, either in the naphtha range or in the diesel range or paraffinic waxes. So basically, how depending on market demand, we can kind of produce the product.
So, Anil, fair to say that C21, 27 will be a diesel, and C35 maybe will be more of an oil?
So C14 to C24 or 27 could be in the diesel range.
Okay. That's material we can put in the car and drive with. Well, not our car, a diesel car.
Yes.
Okay. And it's when we finish the job on this, we have the ability to, people may know the word, the spec or the standard for it. We have the ability to make it to standard, to build it to the standard if needed. Normally, we don't need it to do it. There is, for most of the time, there is some kind of a petrochemical process can take it and continue adding value into the process.
Yeah, so basically, we will need to process a mixed plastic. So in this case, if you want to achieve desirable properties, we will not only process polyethylene, but we need to process a combination of polyethylene, polypropylene, and polystyrene, because diesel has some aromatics into that. So we can kind of use a mixed plastic feed to get like a diesel or any other desired properties.
So it's a chemical hub basically that it can, at the end of the day, based on the waste that is available, provide a solution. And this is the reason why we feel, for example, in Mexico, we can provide diesel to the government that can transport or fuel the public transportation for it. We're not sure that will happen, but that's what we see. It's a very easy jump from where we are to just give them diesel product for their buses, and they will not replace those buses with electrical in the next 20 years or so, whether we like it or not. I think this is one of the last slides. Anil, this speaks a little bit to our ability to move and create different product because of the knobs that we have in the system. Can you speak a little bit about the knobs and how they affect the carbon?
So basically, this is a GC data for one of our product from polyethylene. And if you see, the carbon number ranges from all the way from C7 to C50. And majority of the carbon number is less than C34. So what we can do, like, as I said, like we have different knobs or process parameter. They are temperature, so we can vary the temperature, or we can vary the pressure. The other knob is water to polyethylene ratio, so we can vary that parameter, or we can also vary the time, like how long we are processing the material. So depending on, let's say, if there is a more desire for naphtha product, which is in the range of C10 to C14, so what we will do is, like, we will subject polyethylene for a longer duration at a high severity condition, which will result in the formation of more carbon number towards the lighter end. Or what happens is, if we need like no naphtha, but if we need like some of the diesel products, so we kind of use a moderate or intermediate severity of the product. And if there is a demand for lube oil or paraffinic waxes, which could be used for molding or other purposes as a grease or lubrication agent, so we can kind of tune the process so we produce more of C30 plus compounds.
So with this slide, I want to try to visualize to the owners, what does it mean? So if we process the material, at the end of the day, we can take a bucket and throw all of those carbon chains all together and give it to a refinery, and refinery will deal with it, and it will have a certain value, and currently no less than $800 per ton. But if we will, act a little bit more carefully and add very, I'll say, a small system called distillation column, anyway, just separation column, then based on the tune of the product, we can come up with different product, and they will have different values, and we can sell those values. So again, that speaks a little bit to the flexibility of the technology and the team to answer to customers. Now, most of the current customers that we have, the big boys, they basically care about, I'll say, us commercial aspect of the technology, and that's it. We leave the speciality to them. They don't need us to discuss and to decide what is that they want to produce out of it. They just want a technology that is better than the competitors. But some customers, and this is where you hear many times that, for different territories, you don't see a lot of operation. The reason being is that, it's very cheap. Plastic is very cheap. Nobody wants to collect it and deal with it. But us being able to provide different customers different solution does motivate the customers to look into now profit possible incomes because of that. So it's not just that we're creating something, we actually could create something that maybe cater to specific customers. And when it comes to the territories that are, doesn't have centralized location, doesn't have lots of development, this becomes a really an advantage for us.
And one thing I would also like to add here is, so since our process is a water-based process, so the pre-treatment is very simple. Like, so if there is mud or anything, like, we can wash it and we can use the plastic without the need of drying. But in case of mechanical recycling or pyrolysis or any other thermolytic process, what will happen is there will be an enormous amount of energy required to dry the product. So
just dry the product. Yeah. So sorry, this is a great comment. And so we have a current project in Ontario with a company that has a collection of agricultural waste. This material is basically sits in the farmer side, and these guys are having the largest collection process. And they've seen many technologies. Now, most of the technology that they've seen were required really intense heat to generate just to dry and to clean the material, the feedstock. With us, for us, we don't care if the feedstock, because we're water-based, we don't care if the feedstock is any level of humidity inside. And so we wash it, but we don't need to dry it, and we can move it. The only reason we are cautious about the level of water and moisture, because we don't want to heat too much water in comparison to the material that we're processing. So it becomes an economic issue. But for competing technologies in the space, they absolutely have to dry the material to a certain level before they even start working on it. So again, an example to advantage right there in a farmer's land. In comparison to anything else. And there is, again, I'll refer you to the to the news release where the farmers stated they have been sitting and looking for technologies for the last 10, 15 years. And Aduro is among those that, if not the only one, those that really, really has a potential to do something there in the pharma space.
Ofer, I would also add about wax
Yeah.
papers. So during our visit, we found for burgers or parchment paper, which is basically cellulosic material covered with waxy kind of material. So even that could be used as the feedstock in our process. Right now, there is very limited process which can take them and recycle them. That's a disadvantage for other processes, but it's more like a valuable feedstock for our process. This is a simplified diagram. It's called a block flow diagram for a continuous reactor system for our process. We are not showing like an engineering drawing, but it's more like just the blocks. So you can see what will happen is, say, a lot of raw material like PE, PP, polystyrene, polypropylene. If we can pre-process them. So for example, if there are any metals, sand, dirt, or other contaminants, we can just remove them by cleaning with water. And basically, we can have a floating system where heavy materials or inorganics will settle, and you can take the plastic, which will be fed into our reactor. So our reactor is pretty simple. It's just like a normal hollow reactor system, which operates at pressures and temperature. The temperature is in the range of 300 to 375 degrees Celsius, and pressure is anywhere from 1,000 to 2,500, 3,000 psi, which is basically fed into the reactor. And this is like a back pressure regulator, which is basically used to maintain the pressure of the reactor system. And as the feed process, we will, whatever the amount is going in, you will get the product out. We just take the product, cool it, and collect it in what we call the phase separators. So basically, it lets the liquid product collected at the bottom, and the gas, which is not condensed, or the vapors, are transferred to the next vessel, where you further cool it down. So that way you minimizes the loss of valuable liquid product, and just the gas are kind of released, which could be used for providing energy for the process. And then the product and the water is collected from the second separator. It also has our catalyst dissolved in it, and it could be treated and recycled. So the hydrocarbons which we obtain, basically, as we said, right, like different carbon numbers, those are often we can kind of either sell them directly to the refiners, or we can just post-process it and select the selective components. If you look at this, the process is not very, very complicated, I would say. It's pretty, all the unit operations are straightforward. We don't need anything novel at the front end or the back end. The heart of the process itself is a reactor. Again, it's a standard reactor. We are not using any novel or fancy reactor system. The only difference is how we feed the material and catalyst and our hydrogen source. That's the impacts the chemistry.
So I just again visualize it in what is it we're talking about. So when you guys look at where it's called water and hydrogen source, then if you think of the system as a convey that has different stages, okay, of reaction. And at the front end of it, there'll be some plastic bottles as part of it, and so we will subject the process into certain conditions where we could benefit from the hydrogen donor, for example, and then we'll move on and we'll do our reactions. And as we continue and operating on different severities, we'll subject different material to different stages, and we'll get a different output. So that, by definition, saves a lot of the sorting that is required by competitors, for example. So for us, if the material is contaminated with a little bit of a paper, that's very good for us, because we can use that for our advantage in the system, basically. So by this, I think what I wanted to show is that we are breaking the boundaries that current traditional or legacy systems are working with. They have to do a lot of sorting in order to satisfy the conditions for a system, which effectively at the end of the day increase the cost of the operation. And so now you're starting to run into other issues. You have to secure feedstock, and you have to make sure that this feedstock is, forever and has a certain value, and all kind of other issues. So again, just a demonstration how embedded in the technology, a lot of flexibilities.
So in short, like if there is like so much pre-processing required and you just need to feed one kind of material, then like with that, it doesn't make sense to chemically reprocess it, because now you almost created a single pure stream. So that could be mechanically recycled, right? So with our process, we don't need to pre-process to such extent that where you got a single stream. So we can handle like a mixed stuff.
So in general, there is a lot that we can talk about, but I'm hoping you guys could be seeing how there is, what we try to do is to show you how embedded in the technology benefits are economical advantage that we have in comparison to the environment.
So I hope this was helpful to you. I hope you understand the company Aduro and the chemistry behind it a little bit more. Both of these calls had question and answer sessions. I didn't include them yet because it would make those videos too long. So the next video, which will be published tomorrow, will be a compilation of questions and answers.